Hey Hayden, it's Miss Tracy. This is about lesson 94. Sorry this took so long. I'm using a new software and I'm just trying to kind of figure it out as we go. So the distance problems or the uniform motion problems are the ones that you seem to have the most trouble with in lesson 94. So let's look at what we're talking about with these. So here's the first one. It says an eastbound bus left Ukiah at noon. So we've got to understand what's going on. Right? You've got to be able to pull apart the sentences and see what's going on. All right, so eastbound, that's going to give us, a direction, and it's also going to give us a name for the bus, right? And it left at noon, so it's 12 p.m. So we're going to write those two facts down. So we have an eastbound bus, and actually, I'm going to draw this more in the middle right here. This is noon, or this is the starting point. All right, so your starting point. We have an eastbound bus, and east is going this way. So this eastbound bus left at noon. So he left at 12 p.m. So that's all the information we have for him right now. So now we have 2 hours later. So that gives us our new time. 2 hours later, a westbound bus. So it gives us direction and time. So the 2 hours later, that would be, it was a westbound bus. So it's going the opposite direction from east. So it kind of helps to know like east and west are opposite directions. So north and south are opposite, east and west are opposite. So those are good to know. It's good to know what that is. Your little compass that you have when you're out in the woods. You have north, south, east, and west, right? So if you know that, then that'll help you with that, right? You really need to know your directions in order to answer these types of problems. So you've got your westbound bus. So he's going the opposite direction, and he left 2 hours later. So 2 hours after 12 is going to be 2 p.m., right? So the eastbound bus left at 12 p.m., and the westbound bus left at 2 p.m. And they're going in opposite directions, and they started in the same place. Now, this says, if the buses traveled at the same rate. So what that means is the rate of the eastbound bus is equal to the rate of the westbound bus because of that statement right there. Now we keep reading, and it says, if the buses traveled at the same rate and were 500 kilometers apart at 6, find the rate of each bus. So this point here and this point here, that is 6 p.m. And the total distance between here and here is 500 kilometers. So looking at this picture, I can say that the distance, this is the distance of the westbound bus, and this is the distance of the eastbound bus. I can say the distance of the westbound bus plus the distance of the eastbound bus is equal to 500. Okay, we can see that. At 6 p.m., wherever this bus is to wherever this bus is at the same time is going to be 500 kilometers. All right, so now that we have our picture, we have our starting equation, we have all the information that tells us some values from the sentence, we are going to set up our table. And here's our table. Remember, you have rate, and then we have time, then we have the eastbound bus, and we have the westbound bus. Now, we know the rate of the eastbound bus is equal to the rate of the westbound bus, so we don't know what those rates are. But we know the time of the eastbound bus is from 12 to 6. That's 6 hours. We know the time of the westbound bus is from 2 to 6. That's 4 hours. Okay? So we got to find this and we got to find this. So what we're going to do is we are going to substitute in, we're going to change this to our DIRT, or our distance equals rate times time formulas. So the rate of the westbound bus times the time of the westbound bus. And we do this because D is equal to R times T, right? Our DIRT formula. We can change this to rate times time. Plus distance equals of the eastbound bus is equal to the rate time of the eastbound times the time of the eastbound. That equals 500. Okay? Now, we know the times of each one, and we know the rates are the same. So what that means to me is I can substitute in one for the other. So I'm going to keep RW, and I'm going to put the time of the westbound, which is 4. We're going to multiply those together. And then the rate of the east, I'm going to substitute RW because it's the same. And the time of the east is 6. And that equals 500. So 4 times RW is 4RW. Plus 6 times RW is 6RW. That equals 500. These are like terms because the same variables. That's 10. RW is equal to 500. Now, that's not your final answer. You're going to divide and you're going to find the rate of the westbound train, which is also going to tell you, or the bus, which is also going to tell you the rate of the eastbound bus. I'm going to leave you there, but I want you to understand where we came from. Here is from this picture. Draw the picture to where it illustrates what's going on in the word problem. If you don't draw the picture, you're going to be confused. Take the time to put in all the steps. All right, let's look at the next one. All right, here's the next problem. So let's break it down again. We're going to start with the first part. We're dealing with trains. A train starts from Peoria. So that's our first location, Peoria at 2 p.m. and is going towards Reedley. Okay, so we have, let's draw that bit. We've got a train here, and it starts in Peoria, and that's at 2 p.m., and it's headed toward Reedley. Okay. Now, that is 750 kilometers away. So that's good to know, 750 kilometers. At the same time, a train leaves Reedley. So at the same time, we've got a train coming from Reedley. So that means on the opposite side, over here, this is Reedley, and I got a train headed towards Peoria at the same time, so 2 p.m. It heads for Peoria, and it is going 85 kilometers an hour. So now we have its rate of speed. So we can write that down too. So it's going at 85 kilometers per hour. So we have both of them leaving at the same time. The one from Reedley is traveling at 85 kilometers an hour. Okay. If the trains meet at 5 p.m., what is the rate of the first train? So right here where they meet, this is 5 p.m. Well, if they both left at the same time, when they meet, it's going to be the same amount of time that has passed for both of them. So that tells me that the time of the Peoria train is equal to the time of the Reedley train. So their time is the same, but their rates might be different. So that means they're going to be unequal distances. But we know what the total distance is. The total distance, we were told earlier, was 750 kilometers from Peoria to Reedley. So there's our picture. We have a Peoria train leaving at 2, and it's headed toward Reedley, which is 750 kilometers away. We have a Reedley train leaving at 2, headed toward Peoria, and it's going at 85 kilometers an hour. They meet each other at 5 p.m. So now we can make our table. So we have the rate and we have the time. We have the Peoria train and we have the Reedley train. Now we know the rate of the Reedley train is 85. We know the time for both of them is 3 because they left at the same time, they met at the same time. So all we don't know is the rate of the Peoria train. But what we can see here is that the distance of the Peoria train plus the distance of the Reedley train is equal to 750 kilometers. So the distance of the Peoria plus the distance of the Reedley is equal to 750. Now we can break that down into our dirt formula. So the rate of the Peoria times the time of the Peoria plus the rate of the Reedley times the time of the Reedley is equal to 750. Now we know the time for both of these is 3. And we know the rate of the Reedley is 85. So 3 times the rate of the Peoria train, that's an R, plus 85, which is the rate of the Reedley, times 3, which is the time of the Reedley, is equal to 750. So from here, I want you to solve it for this train. But this is how you're going to put it together. You look at your picture and you see this is the distance of one plus the distance of the other equals the total distance. And then you break it down into your distance is equal to the rate of whatever times the time of whatever. So the rate of the Reedley times the time of the Reedley would be the distance of the Reedley, right? The time of the Peoria is equal to the rate of the Peoria, or I'm sorry, the distance of the Peoria train is equal to the rate of the Peoria times the time of the Peoria. That little letter on the bottom right here distinguishes between the two different vehicles, the two different trains. And that's what we do here. We look at our picture to write the overall equation, and then we break it down. And then we substitute in the information that we know, and then we solve for what we don't know. Every single time, that's what we're doing. So solve this and give me the rate of the Peoria train. Let's do the next one. All right, so here we've got 2 ships, and it gives us a total distance. I don't know why I used that one. I meant to use this one. Gives us a total distance. They were 700 miles apart at midnight. So I can draw a picture here. I've got these 2 boats. I've got the fast boat over here and the slow boat over here. And they are a total of 700 miles apart. That's their total distance. And at midnight, so 12 a.m., that's where they were, 700 miles apart. So that's a picture of the first sentence, right? Now we're going to adjust it as we go. Now they're headed directly towards each other. So what that tells me is my arrows are going towards each other like such, and they're probably going to meet. So actually, that's probably reversed because the fast one is going to go further than the slow one, right? Let's put him here. Let's put him here. Then they're going to meet. If they collided at 10 a.m., so this time right here, this is 10 a.m. Find the speeds of both ships if one was traveling 30 miles per hour faster than the other. So one was 30 miles per hour faster. So let's make our table. So we've got the rate and we've got the time. We've got the faster one and the slower one. Okay. So the time of both of them is the same from 12 a.m. or I'm sorry, from 12 a.m. to 10 a.m. That's going to be 12 p.m. No, it's 12 a.m. Midnight is 12 a.m. So 10 a.m. is going to be, it's kind of weird how that works, right? That's going to be 10 hours. So our time is 10 for both of these guys. We don't really have to do any math. From 12 to 10, 12 to 10, that's 10 hours. So we can go ahead and write our equation that the distance of the fast one plus the distance of the slow one is equal to 700. We can see that right away. The distance of the fast plus the distance of the slow is equal to 700. Right? The time of both, actually, I'm not going to do that here. I'm just going to do that up here because then I don't lose this space. So now let's think about it. Let's think about their speed, their rate. So if the faster one is 30 miles per hour faster than the slow one. So that means we're going to take the speed of the slow one and add 30 to it. So that's what the speed of the faster one is, right? The rate of the faster one is the rate of the slower one plus 30 miles per hour. That's what we need to write. Let me rewrite that better. The rate of the faster one is equal to the rate of the slower one plus 30 miles per hour. That's what this means right here. 30 miles per hour faster. That's the faster boat. So now we have an expression for the faster one, and the slow one is still just the rate of the slow one. So we can turn this into the rate of the faster one times the time of the faster one plus the rate of the slower one times the time of the slower one, still equal to 700 miles. Now we can drop in what we know. We know that the time is the same for both of them. So the rate of the faster one is the rate of the slower one plus 30, right? And the time is 10. The rate of the slower one we don't know. We know the time is still 10. So from here, you should be able to distribute 10 times RS, 10 times 30, plus RS times 10, and solve for RS, which then you substitute in here to find RF. And that's all of that I'm going to do for you. So look at your problem, right? Look at how the words, the numbers in here, give you the pictures of the puzzle. Okay? It gave us this. It gave us this and this. It gave us this bit, right? Look at how it's broken down. All right, let's do the last one. I think there's only one more. All right, so this is the last one. And this one is almost exactly like the previous problem. So let's highlight our information. So the cars were 300 miles apart, again, with the pen and not the highlighter. I do that all the time. So the cars were 300 miles apart at noon. All right, so there's our picture. We've got a car on this side and a car on this side, and they are 300 miles apart. That's their distance. And at noon, that's 12 p.m. At noon, that is where they were. They were 300 miles apart. Okay? So apparently we have a fast car and a slow car. So let's put the fast car over here and the slow car over here. All right, so they were headed directly towards each other. So that tells us how to draw our picture. So directly towards each other. The fast one's going to be a little bit closer than to the slower one. It's not going to be right in the middle. Doesn't matter though. It's just a drawing. If they met for a picnic at 3 p.m. Okay, so if they left at the same time and they met at the same time, then their times are equal. So from 12 to 3 would be 3 hours for the fast one, and from 12 to 3 would be 3 hours for the second one. Now, if one was traveling 10 miles per hour faster than the other, that's going to be our faster car. So the rate of the faster car is going to be the rate of the slower car plus 10 miles per hour. Right? Now, based on our picture, we can see that the distance, this is an F, by the way, of the faster car plus the distance of the slower car is equal to 300. So we can write that as our equation. The distance of the fast car plus the distance of the slow car is equal to 300. Now we break that down. The rate of the faster car times the time of the faster car plus the rate of the slower car times the time of the slower car is equal to 300. Now we can just drop in the information that we have. We know the time is the same for both of them, and the rate of the faster car is equal to this. So we put that in, RS plus 10 times the time of the faster car, which is 3. Then we don't know what the rate of the slower car is, but we know the time is 3. Still equal to 300. So from here, you should be able to distribute, get rid of your parentheses, distribute, add like terms, and then solve for the rate of the slower car. When you find the rate of the slower car, put it in here and add 10 to it, and that'll be the rate of the faster car. Okay? Pay attention to the language in the problem and draw the picture. If you don't draw the picture, you're going to be confused. The picture helps you to write this, and it also helps you find your times, right? Once you see what's happening, then you're going to understand what's going on so much better than just trying to imagine it in your head. Don't try to hold everything in your head, okay? That's why God invented pencil and paper. Sketch out a diagram of what's going on. Give us a sketch of the picture so that you can wrap your head around what needs to happen in your formula. All right. I am not giving you the answers for any of these. I'm going to let you solve them on your own. I hope that helps you to understand where you need to go with these. Draw the pictures. Okay. I'll talk to you next time. If you need more help, always feel free to ask, and I will get back to you as soon as I possibly can. Bye for now.